Hello, I'm Aki Singhania from Definity, and today we will be discussing how the Internet computer manages and executes applications. On the IC, applications are called canisters, which really are an evolution of smart contracts as seen in other similar projects. Currently, canisters can either be written in Rust or in Motoko and then compiled to WebAssembly. In fact, any language that can be compiled to WebAssembly can be used with the appropriate bindings. To properly understand canisters in detail, let's first discuss the motivating example of a set of applications running on the IC. Let's say that there exists a travel agency canister, some hotel canisters, and some airline canisters that work together to serve users trying to book trips. These canisters could be structured like message passing processes in classical RPC systems, where they make progress by executing and sending messages to each other. Then the user would send a message to the travel agency asking to book a hotel and a flight. The travel agency would then send messages to various hotels and airline canisters trying to find the best deal, then book the trip, and then finally reply to the user. If we dig further into this example, we can see some common problems that the developers of such canisters may be faced with when writing them. It can be the case that some hotels or airline canisters are buggy, and when processing a request from the travel agency, they fail to produce a response. This can make aggregating the responses on the travel agency complicated. Classically, in such situations, the travel agency would use timeouts and have to do a trade-off between setting the timeout too short, missing valid replies, and setting it too high, making it less reactive to faults. Instead, if the platform could guarantee that if a canister fails to respond, then the platform will generate a response on its behalf, then that would make writing the travel agency canister simpler. Another potential problem could be that the hotel canister could crash after committing updates to its dataset of free rooms, but before completing the transaction. This could potentially cause resource leakage. This problem could be alleviated if commits to canister states only happen if they manage to execute messages successfully. Next, these canisters will be running on top of a shared platform that is the Internet computer. The platform will share its compute, storage, and network bandwidth resources between the canisters. The IC should share these resources between them in a fair manner, and as some of these canisters can be competitive with each other, long-running canisters could try to use an unfair share of the resources. In such scenarios, a feature like time slicing from classical Unix-like operating systems, where long-running processes are interrupted to let others run, would result in a fair utilization of the resources. Finally, these canisters have to pay for the resources that they're using on the platform. In many classical cloud computing platforms, the developers of these applications have to estimate their potential utilization ahead of time and run the risk of renting too much or too little capacity. Instead, if the canisters can be charged precisely for their actual resource utilization, and resource reservation was an optional rather than a necessary feature, that can alleviate some of these problems. In this talk, we will be discussing how the IC can help make writing these canisters easier by offering solutions to the above problems. We discussed that canisters on IC make progress by sending messages to each other and would like to have a guarantee that when they send a request to another canister, they will eventually get a response. The IC provides this guarantee by tracking for each canister a list of call contexts. Each time a canister executes a request, a new call context is created in its system state. The call context tracks how many requests the canister has sent for which it has not yet received a response. When a canister executes a response, the relevant call context is kept up to date, and if the canister sends out further requests, they are also added to the call context. The call context additionally tracks if the canister has responded to the original request yet or not. In the case where the context has no more outstanding requests and the canister has not yet responded to the original request, the IC can correctly deduce that it is impossible for the canister to produce a response, and it produces one on its behalf. When we discussed the problem of sharing resources fairly between the different canisters, we saw how this is a similar situation as in Unix. There are actually a few more similarities between the two that are worth discussing now. Applications in Unix are called processes, and they consist of two types of states: a user state that they have direct control over, and a kernel state, access to which is mediated by the OS. The kernel state stores sensitive data that the application cannot be allowed to manipulate directly for secure and correct operation of the system. Applications can only access and modify this state via system calls. Canisters similarly have an execution state and a system state. The execution state contains things like the canister's wasm heap and globals. Canisters have complete control over this data and can modify them freely. The system state consists of sensitive data like the canister's cycle balance, its ID, message queues, schedule-related data structures, etc. Just like in Unix, access to this state is mediated via system calls. Also, just like Unix, canisters are scheduled on the IC. We use a priority-based fair scheduler. A canister can have a priority between 0 and 99, where the number indicates in percentage roughly how much of a subnet's single compute core the canister has reserved. Over several rounds of execution, the canister is guaranteed to get that much of the compute resource as long as it has sufficient work to do, that is, messages to execute. If a canister asks for 0 priority, then scheduling is best effort. Canisters that ask for a non-zero priority have to pay for it, and a canister's priority can be seen as how many resources it has reserved on the IC. The scheduler is also fair in the sense that when two canisters have asked for the same priority over multiple rounds of execution, they will get a similar share of the compute core as long as they have sufficient work to do. Now that we have seen how canisters are scheduled, let's see how they actually execute messages. A message sent to a canister consists of, amongst other things, the name of the function in the wasm module to be executed, along with a list of arguments for the function. Executing a single input message on the canister consists of the following steps. Give access to the execution state along with the name of the function to be called to the wasm embedder. During execution, the canister can then look up the list of arguments from its input messages via system calls. The canister can also optionally produce additional messages for other canisters via system calls, making updates to its system state. At the end of the message execution, the wasm embedder produces an updated execution state, and we have access to the canister's old and modified execution and system states. If the execution succeeded, then the modified states are retained. And if execution failed, for example, because a canister performed an illegal operation like divide by 0 or used a system call in an invalid way, then the canister state is rolled back. That is, the old states are retained. The next time the canister executes a message, we use its updated system and execution states. This means that any changes the canister makes to its heap in previous successful executions are visible to future executions. This feature is called orthogonal persistence, and it frees the developer from having to worry about persisting data in between message executions, as the system will persist all changes to the canister's heap. It also addresses the problem we discussed earlier of developers having to worry about only committing state upon successful message executions. Canisters must pay for all the resources that they use on the IC. The currency of payment is called cycles, which is an IC-specific token, and each canister has a cycles account in its system state for storing them. At regular cadence, the IC will deduct payments from this account based on the calculated resource consumption of the canister. A developer can procure cycles to replenish the canister's balance in a number of ways, including by converting ICP tokens to cycles. When a new wasm module is installed on a canister, we instrument it so that we can track how many wasm instructions the canister has executed. This instrumentation is done by adding wasm instructions to the module at specific intervals that count how many instructions have been executed since. At the end of a message execution, we have a precise measurement of how many wasm instructions were executed, and we can charge for them accordingly. We also track how much storage the canister is using on the IC in the form of canister's wasm module, heap, globals, etc., and charge for them on a regular cadence. Next, we also charge canisters for sending messages to each other. In this way, we charge canisters for all the resources: compute, storage, and network bandwidth. So far, we discussed canisters by comparing them to other systems like our PC systems, Unix, and cloud computing platforms. However, there are certain features of the IC that sets it apart from these projects, which we should now cover before we can continue discussing what additional functionality it offers to canister developers. The IC is really a collection of subnets, where each subnet hosts some set of canisters. As more canisters are installed on the IC can bring up additional subnets to meet the demand. The subnets operate independently of each other, allowing the IC to scale. Each subnet in an IC is further a collection of nodes. For security, when a canister is installed on a subnet, a copy of it exists on every node on the subnet. Each node manages a fully replicated state for the subnet that consists of, among other things, the state for all the canisters that are installed on the subnet. For the correct and secure operation of the IC, all honest nodes on the subnet must update their replicated state in an identical manner. This includes updates made to the replicated state when a canister executes a message, determining the precise amount of resources that the canisters have used, figuring out how much they should be charged for these resources, etc. Subnets on the IC make progress in the following manner. At the beginning of the round, all honest nodes on the subnet start with the same state. Consensus on each honest node comes to an agreement on and then delivers a batch of ordered messages to execution. Each node applies this batch on the state to compute a new state for the end of the round. In order to ensure that each node computes an identical state, the application of the batch must be deterministic and identical on all nodes. This means that the nodes cannot use any non-deterministic information such as local time to influence execution, as that could result in different nodes computing different states. The deterministic execution of a round consists of the following steps. First, induct all the messages in the batch that consensus delivered to the input queues of the canisters. Then, compute a schedule of which canisters should be executed in this round. Then proceed to execute the canisters till either they run out of messages or have been executed for a predetermined maximum duration. Finally, invoke the message routing component to process any output messages that the canisters may have produced. We said earlier that a feature like time slicing is important to ensure that a long-running canister cannot hog the system for too long. In order to properly implement this feature, we would need to do something like the following. First, measure a canister's execution duration. Second, interrupt it when it has surpassed some set limit. Third, checkpoint its state at this point in time, allowing other canisters to make progress. Finally, the next time the suspended canister is scheduled, continue its execution from where it left off. In order to ensure that all nodes always compute the same state at the end of message execution, we must interrupt the canister at precisely the same point in execution on all nodes. This means that if we use a straightforward technique like a local stopwatch to measure the canister's execution duration, due to the inherent non-determinism in how many instructions different CPUs will execute in the same amount of time, nodes may end up interrupting canisters at different points in execution. Therefore, instead of measuring actual time, we measure how many WASM instructions the canisters have executed and interrupt it when it has hit a set limit. Note that this is actually the same mechanism that we also use to figure out how many WASM instructions the canister executed to charge it for the resources consumed. With this mechanism, we are guaranteed that even if different nodes take different amount of time to execute the same number of WASM instructions, we are sure to interrupt execution after a deterministic number of instructions have been executed, and hence guaranteed to have the same state on all nodes after execution finishes. The next bits of functionalities of suspending the canister's execution and resuming it later have currently not been fully implemented. Implementing them is on our roadmap, so for the time being, we treat canisters that hit this limit as having performed an illegal operation and roll back their state. I hope this presentation has given you a good overview of how applications in the form of canisters are managed and executed on the IC. We first saw that canisters are like processes in a classical RPC system, where they make progress by sending each other messages and by executing them, while relying on the guarantee that each request will eventually receive a response. We also saw that the canisters are like processes on classical Unix-like operating systems, where they have an execution state that can be directly modified by them and a system state that can only be accessed via system calls. In this context, we discussed orthogonal persistence, where the IC retains modifications to the canister states in between successful executions so that the developers do not have to worry about persisting state modifications in between executions. Further, we also discussed how the IC provides additional OS-like functionalities like scheduling and interrupting long-running canisters to implement time slicing. And finally, we also covered some unique properties of the IC and how it is able to charge precisely for the resources consumed.